All right, welcome back to Chapter 8, Tests of Hypothesis. Now we're going to look at Section 8.4. In Section 8.4, we're going to put it all together, and we're going to look at a situation when we have a test of hypothesis about a population mean using the normal z statistic. All right, so in hypothesis testing, we have this long procedure, long process, yeah, it doesn't make a lot of sense in isolation in Section 8.1, 8.2, 8.3. Until you put it all together and look at some examples. So that's what we're gonna do here in 8.4. All right. So in terms of the whole procedure, here is the official textbook stuff. All right. This is the template, the recipe for a large sample test of hypothesis about mu based on a normal z statistic. So why do we say here based on a normal z statistic? Well, the reason why is because x bar, the statistic x bar that we use to make an inference about mu, it follows a normal z statistic as long as the sample size is large. If the sample size is large, then we can analyze the distribution of x bar. We can predict its behavior using the normal distribution. And the reason why, again, is because of the central limit theorem. All right? So we're going to use x bar to know about mu, to know about a test of hypothesis about mu. All right? So our test statistic here, if sigma is known, then we take what our statistic x bar, we subtract off the value that we're hypothesizing mu to be, and then we divide by the standard error. All right. If sigma is unknown, which is most likely the case, but we have a large sample size, then we just substitute in the sample standard deviation, and because of the central limit theorem, we end up having a valid inference. All right. So if we have a one-tailed test, all right, we can test whether or not mu is less than some number, or if mu is greater than some number, right? This is a left-tailed test, this is a right-tailed test. Or we could have a two-tailed test. In that case, we just say that there's a strict inequality. We're trying to show that mu is just different than some number. All right, so in terms of forming the rejection region, if we have a left-tailed test, then the rejection region is formed on the left side of the distribution. If we have a right-tailed test, then the rejection region is formed on the right side of the distribution. And if we have a two-tailed test, then what we're saying is our rejection region is split up to both sides. That's what the inequality is representing here. In other words, if we get either an extremely negative test statistic or an extremely positive test statistic, that's when we'll reject the null hypothesis. We'll see an example of that in a moment. All right, and then in terms of the p-value, all right, the p-value approach is will have the same inference as the rejection region approach, the same decision, all right, but the p-value here is again on the left side of the distribution for a left-tailed test. The p-value is on the right side of the distribution for a right-tailed test. And again, we just double our p-value if we have a two-tailed test. We double our area. And the p-value is again defined as the probability under the assumption the null hypothesis is true of finding a test statistic as extreme or more extreme than the one we saw in our actual sample. All right. So here's how we make our decision. All right. If our p-value is less than alpha, we reject the null hypothesis. Okay, so there's a lot of notation here, textbook notation, but again, these things don't make too much sense until you see it in the context of some examples. All right, so conditions required for a large sample hypothesis test about mu, we often want to consider, okay, what conditions are required? What is the fine print here? All right, so number one, a random sample is selected from the target population, and then two, our sample size is large, i.e. n is at least 30. This way, the central limit theorem will hold. Okay, so our possible conclusions are always going to be either reject the null hypothesis, that's one option. We reject the null hypothesis if our test statistic is weird. That's it. That's basically it. All right. We don't reject the null hypothesis if the test statistic is not weird. That's it. All right, let's jump forward to our actual example. All right, so this is example part 1 of 2. All right, scientists want to know if the mean number of close friends for people who have a truck is more than 9. All right, so right there, in this simple statement, okay, we actually have the parameter that we want to know about, and we have the number that we want to know about as well. The question is, what are we testing here? Do we have a left-tailed test or a right-tailed test? Well, here we say that we're looking to know if the true mean is more than 9. More than 9. So consider for a moment what statistics would provide evidence, what statistic I should say, if we went out and sampled a bunch of people with a truck. All right, if we went out and sampled a bunch of people with a truck, what value of x bar would provide evidence that the true mean was more than 9? It would be numbers that are more than 9. The question is it larger? Is it larger than 9 by some amount, some magnitude, where we can officially say overall for the whole population, make an inference and say it really is more than 9. So the farther away x bar is from 9 in the positive direction, the more evidence we'll have that, you know what, we're actually going to be concluding that it really is more than 9. All right, so let's say we went out and got 35 people and we got an x bar of 10.62 and we got a sample standard deviation of 3.03. Conduct a right-tailed test at alpha of 5%. All right, so this is the whole hypothesis testing thing. Here it is. This is the problem. This is what they all look like. Take out the window dressing. All right, maybe some of the fluff in my stat lab. All right, this is what they look like. All right, we have a value that we're testing relative to a particular parameter. All right, and then we have sample data. And the question is, do we have enough evidence to say that it really is more than 9? All right. Now, we're making a decision at some level of alpha, and we'll talk more about that in our next video specifically, but here let's just follow the mechanics of what the hypothesis test procedure is stating. All right. So what are the null and alternative hypotheses here? So the null hypothesis is that mu equals 9. Remember, the null hypothesis will contain a statement of equality. All right. The alternative hypothesis here is that mu is greater than 9. We need a strict statement of inequality here. Okay. Greater than 9 is a strict statement of inequality. All right. So let's form our rejection region. All right. Our rejection region is based on our level of alpha. All right. In the problem, and we're going to reject the null hypothesis here, if the value that we compute from our test statistic is to the right of the z-score associated with the level of alpha in the problem. All right. The level of alpha in the problem was, back it up here, it was alpha of 5%. All right, so we have a right-tailed test, so we need to trap 5% on the right side of the distribution. What z-score is that associated with? The answer is it's 1.645. All right, you can see that from the table. It's also a working backwards problem from way back in chapter 5. All right, if you look at this picture right here, all right, this is 5% area. So to communicate with our table here, our table is in our pink probability table packet from before the coronavirus. All right, to communicate with that table, we'd have to look in the body of the table for 0.4500. If you look in the body of the table for 0.4500, figure out which z-score is closest to that, what you'll end up seeing is that that value is 1.645. All right, so what that means here is we're going to reject the null hypothesis if our test statistic that we calculate is greater than 1.645. That will give us permission to reject the null hypothesis. All right, so that forms our rejection region. What about the test statistic? All right, so that's what we have to calculate now. We're going to standardize the x bar we found in the problem. The x bar we found in the problem was 10.62. Clearly 10.62 is more than 9. Clearly it's more than 9, but we can't decide just on the basis of a sample if it really is more than 9 for the whole population. Okay, unless 10.62 is what we end up calling in this course statistically significant. That means it's so far away from 9 that we can't just attribute it to the fact that x bar varies. Okay, so here's our test statistic. All right, z subscript c equals the statistic we got minus a hypothesized value of mu. All right, that's just the number that we see in either the null or the alternative hypothesis. It'll be the same number in both cases. And then we divide by the standard error, the spread in the sampling distribution of the statistic. All right, so here was the problem originally, all right, and we just got to plug things in, substitute in. And what you end up seeing is that in the numerator we get 1.62, and then we divide by 0.512, which is how much spread is in our new normal curve that we're analyzing since chapter 6. All right, so we end up getting 3.16. So is 3.16 more than 1.645? It is. So we reject the null hypothesis because we're in the rejection region. We're in the rejection region, right? We're all the way over here. 3.16 is way over here. That's in the rejection region. All right, so we reject the null hypothesis. That means that we're crossing out this piece, x. Cross it out, reject it. We're falsifying that, if you will. And that means that we're left with one other hypothesis, and it's that mu is actually greater than 9. All right, so there is sufficient evidence. The true mean number of friends for truck owners is more than 9. So if you have a truck, you're more likely to have more friends than the normal person. All right, so I Googled to get this baseline value of 9. I just Googled how many close friends am I supposed to have, and it said 9. All right, so that's where that 9, that baseline came from here. All right, so here's part 2. Again, the same setup in the problem. It's just that here we're going to use the p-value method. We're going to use the p-value method here. All right. So conduct a right-tailed test at alpha of 5% using the p-value method. All right. So our null and alternative hypothesis are the same as what we just saw. Mu is greater than 9. All right. Here our test statistic is the same thing. It's actually still 3.16. All we're doing here is just switching up the method by which we make a decision. That's not changing our test statistic. In fact, the whole problem looks the same. All right, so here's our test statistic at 3.16, and if we want to calculate our p-value, what we do is find the area to the right of 3.16. All right, we find the area to the right of 3.16, and we see that that area is really tiny. It's 0.0008. So our decision here is to reject the null hypothesis because our p-value is smaller than alpha. All right. What that means for us is that it would be impossible to be committing a type 1 error more than 5% of the time. So we say here there's sufficient evidence the true mean number of friends for truck owners is more than 9. All right. This is the same conclusion we reached using the rejection region method. It's just that now we used a different method that's called the p-value method. All right. Either decision, as long as we stay consistent with our alpha, will lead to the same conclusion. All right. In general, if the p is low, reject the ho. That means that p being low, all that means is it's actually less than 5%, right? 0.0008 is less than 5%. All right. So what that really means is, if the null hypothesis were true, if it really were 9 friends on average that truck owners have, it would be really, really weird to get the X bar we got. 10.62 would be really strange. In fact, it would only occur around 8 and 10,000 times. That's what this probability is representing right there. That is the p-value.